Let's look at the acidity of the alpha carbon. This figure is also seen on page A12 of Ogilvie's mechanistic pattern textbook. Recall that strong acids have lower pKa's and give more stable bases, or weaker bases. So, with these four different carbonyl functional groups, the aldehyde on the far left has the lowest pKa for the hydrogen on the alpha carbon. The hydrogen next to the carbonyl is a poor electron donor. The next structure is a ketone with a pKa about 20 for the hydrogen on the alpha carbon. Remember that the alkyl group donate electrons through the inductive effect, and it will destabilize negative charge on the base. The other two functional groups are an ester and an organic amide. These functional groups have a heteroatom that provide lone pair electron donation through the pi resonance delocalization. The oxygen on the ester and the nitrogen on the amides are good electron donors. In summary, the presence of electron donors next to the carbonyl will destabilize the base and increase the pKa of its conjugate acid. The electron donation can occur by the inductive effect or the resonance effect. Deprotonation of the alpha carbon with LDA. LDA is lithium diisopropylamide and is a very strong base. To prepare LDA, diisopropylamine with a pKa of about 36 is treated with N-butylene at -78 degrees Celsius in an acid-base reaction. The product is LDA and butane. Butane has a very high pKa of about 60. LDA can be stored in an inner atmosphere such as argon in a gas-sealed container or in a glove box. Alternatively, it can be prepared fresh prior to using. Like the Grignard reagent, LDA is sensitive to water or any polar protic solvents like alcohol. It reacts violently with water, which has a pKa of 16, to give the diisopropylamine. LDA, strong base to make enolate ions. The pKa of esters are about 25, and LDA is a very strong base that will deprotonate the hydrogen on the alpha carbon. Similarly, the organic amides have a pKa of about 26, and the LDA is a good base to deprotonate the hydrogen on its alpha carbon. The ester enolate ion and the amido enolate ion have resonance structures with the respective carbanions. On formation of the carbanion or the enolate ion using a weak base for aldehydes and ketones, or using the strong base LDA for aldehydes, ketones, esters, and organic amides, both the carbanion and the enolate ion give the same product. So the carbanion reacting with the electrophile is best to use to predict the structure of the product. The enolate ion is mechanistically more correct.